We expanded the sample spaces. Now we need to add probabilities or assign probabilities to those new expanded spaces. In this case, we've got a city that has 12 partitions, and in each partition, the population is the same. This is a way of illustrating what is called a uniform distribution, because the probability of the drone landing in each of the regions is the same. So how do we assign probabilities? Okay, so for each of the regions, which is one possible outcome in the sample space and reflected by the little omegas. So the probability of the drone landing in omega 1 is 1/12, because there is 1 in 12 regions possibility. And the same is for omega 2, 1/12, omega 3, 1/12, and so on and so forth, up to omega 12. Now, if we want to generate or define a random variable x, we can do that. So we assign 0 to variable x if the drone lands in omega 1. We assign 1 if drone lands in omega 2. We assign 2 if it lands in omega 3, and so on and so forth. So then we can assign probabilities to the random variable x. So what's the probability that the random variable x takes the value 6? Well, that's the probability that the drone lands in omega 7. And that's 1/12. Or 0.0833. What's the probability that the random variable x takes the value 10? Well, that's the probability that the drone lands in omega 11, which is also 1/12, or 0.0833. But in those cases, we consider elementary outcomes. But we can have events that have more than one outcome, more than one omega. For example, what's the probability that x takes a value lower than 4? Well, the values that can take then is 0, 1, 2, or 3. That corresponds to omega 1, omega 2, omega 3, and omega 4. So basically, we need to add all the probabilities for each of these regions. So that is m of omega 1 plus m of omega 2 plus m of omega 3 plus m of omega 4. So each of those one is 1/12. So we've got 4 of them, so it's 4/12, or 0.3333. Now, this is the case in which we don't have partitions in the city, and we measure in the distance from the westmost post of the city to the eastmost post, goes from kilometer 0 to kilometer 12. Now we are going to use these to explain a new type of probability. Until now we were talking about probability mass. We were saying probability. When we use the generic word of probability, typically we are referring when we use the generic word probability, by context, we know whether it is probability mass, which is probabilities for discrete variables, or if it is a probability density, which is probability for continuous variables. So here we have a continuous variable, and in continuous variables, the probability for the drone to land at a specific point, or for a random variable to take a specific value, is actually 0. Why? Well, because there are infinite number of values, and if you divide the total probability, which could be 1, among infinite number of values, then you get infinitesimally small point in the city, and we cannot add any probability to that. So instead, we have to assign probabilities or a probability mass to an interval. And for example, the interval between 3 and 4, or the interval between 3.54 and 6.78. And for those intervals, we can assign a probability. Now, if we make the intervals very, very small, like the interval between 3.55557 kilometers and 3.55558, very tiny interval, then it is almost as assigning a probability to the value between those two numbers. In fact, that's what happens when we calculate the probability for that space, for a small space, then we make it smaller and we calculate the probability for that smaller space, and again and again and again and again and again. There is a point in which, by reducing the space, we don't gain in precision. So when that happens, then that is a reasonable way to assign a probability to that small space. Because the length of the intervals is different, so this exercise of reducing the space to assign probability to small spaces, in some cases we may need to reduce more than in others. So for that reason, in order to be able to compare different things, it's useful to calculate the probability density, which is the probability mass of the interval over the length of the interval. And then we come with a measure of probability that now, if in probability mass you add the probability mass of all the possible outcomes in a sample space, that must be 1. Now in probability density you don't add to 1, you integrate to 1. I'm not going to explain integration. We're just going to show some examples of probabilities. For example, this is a very imprecise way of determining probabilities in this case, but the probability of the random variable x to take the values in the interval between 0 and 1, it's around 0.19. Following this this representation of the CTZ. And the probability of the random variable x to take values in the interval between 1 and 3, it's approximately 0.32. This centered example, we can do the same as before. So what's the probability of the random variable x to take the values between -1 and 1? And that's 0.41. The probability of taking values between -2 and 2 is 0.69. And the probability of the random variable x to take the values -3 to 3 is 0.86, or approximately that. Now, the way we were representing these continuous variables is not appropriate. The discrete variables was okay, but the discrete variables is not appropriate, because when we use probability density, because we are assigning a probability to very tiny spaces, then we form a curve rather than these bars that we were using. So that is the way of assigning probability densities, and this is what we call a normal distribution, in which it is a symmetric distribution with a peak in the center of the distribution. Okay, in that distribution, the probability of the random variable x to take the value, any value within the interval between -1 and 1 is approximately 0.6882. The probability of random variable x to take any value between the interval -2 and 2 is approximately 0.954. And the random variable, probability of the random variable x to take any value within the interval between -3 and 3 is approximately 0.996. This is a case in which the city is partitioned in two ways. One, based on the geographical region, A, B, C, or D, and the other whether the each region has a coastal subregion and an inland subregion. So we define event A as omega 1 or omega 2. So A is the drone landing in each of these parts of region A. B is the drone landing either in omega 3 or omega 4, C in omega 6 or omega 5 or omega 6, and D omega 7 or omega 8. We define the event yellow as the drone landing either in omega 1, omega 3, omega 5 or omega 7, and the event blue as the drone landing either in omega 2, omega 4, omega 6 or omega 8. So now we can obtain the probability for each of those events. So the probability that x equals A equals 0.4. The probability that x equals B equals 0.3. The probability of x equals C equals 0.2. And probability x equals D equals 0.10. That follows our original example, in which we have 400,000 people in region A, 300,000 people in region B, 200,000 people in region C, and 100,000 people in region D. Now, what's the probability of x taking the value yellow? Well, it is 40%. It adds the probability for omega 1, the probability for omega 3, the probability for omega 5, and the probability for omega 7, and that's 0.4. What's the probability of x taking the value blue? 0.6. That means that that's the sum of the probabilities of omega 2, omega 4, omega 6, and omega 8. Now, we can introduce here conditional probabilities. So, what's the probability that the drone landed in region A, or that the variable x takes the value A, given that we know that the drone landed in a blue region? So basically, conditional probabilities are very difficult to process. There's a lot of research that shows that we have a lot of difficulties with dealing with conditional probabilities. So we need to be go very slowly here. So this vertical var means conditional on or given that. So basically that means that x equals blue is something that happened, or something we assuming it will happen, or it happened. So let's say that we get the information, someone tells us, oh, I saw the drone landing in a coastal region. Okay, so do you know if it landed in A, B, C, or D? No, I don't know. Okay, so basically we have this information. It landed in a blue region. That means it landed either in omega 2, omega 4, omega 6, and omega 8. So when we have that information, now the sample space is reduced. It doesn't include omega 1, omega 3, omega 5, and omega 7. So it's a smaller sample space. So what's the probability now that the drone landed in A, given that we know it landed in blue? Okay, so if we obtain the total probability of these four elements of the sample space, and then the probability of this space, then the probability of this space over the total probability, that is the conditional probability. You can see it also graphically. If you stack omega 6 onto omega 4 and omega 8 on top of omega 6, then you will have the same size. So that means that omega 2 is 50%. So when we know that the drone landed in blue, there is a 50% chance or 0.5 chance that it landed in A. Now, this second one, what's the probability that X took the value A, given that we know it landed in yellow? So now it's another time someone tells us the drone landed in an inland region. Do you know where? In A, B, C, or D? No, don't know. So the question is, what's the probability that it landed in region A? Well, now we have to add omega 1, or the probability for omega 1, the probability for omega 3, the probability of omega 5, and the probability of omega 7. So these four elements are what constitute the new sample space. It's smaller than the sample space with 8 outcomes. So basically we divide the probability of omega 1 over the probability of omega 1, omega 3, omega 5, omega 7, and that gives us 0.25. Now, this seems very similar to the previous one. So what's the probability that the drone landed in blue, given that we know it landed in A? So now, that's why conditional probabilities are very difficult. This is nothing to do with the previous one, which is the probability of the drone landing in A, given that we know it landed in blue. So, how is that? We know that the drone landed in A. So now the sample space is omega 1 and omega 2. We stop considering the other 6 possibilities. It's either in omega 2 or omega 1. So, given that we know it landed in A, what's the probability that it landed in blue area? Well, it's 75%. You have these areas, we have 300,000 people, and in this area 100,000 people. So that's 75% or 0.75. What's the probability that it landed in yellow, given that it landed in A? Okay, it's 25%. If it is, this one is 75, then this one is 25. To add to 1. Now, the last case, the expansion by adding number of landings. Okay, so let's consider 3 landings. And in this is a city with 2 partitions, and partition A has 60% of the population, partition B 40% of the population. So the probability of landing in A is 0.6 and probability of landing in B is 0.4. Now, we consider 3 landings, and the sample space, big omega, it's composed by these 8 possible small omegas. First landing in A, second landing in A, and third landing in A. First landing in A, second in A, third in B, and so on and so forth. So all the possibilities of landing in A or B in the 3 landings. Now, we are not interested in the probabilities of landing in A or B per se. We generate a random variable that is interested in knowing how many of the landings were in A. So it's a completely different variable. The previous variable will tell is the probability of landing in A or B, and which is the probability of landing in a specific region. Now the new variable is how many times it landed in a specific region. What's the probability of landing in a specific region. Okay, so how do we do that? First, we define the random variable we are interested in. This x takes 0 if no landing in A after 3 landings. X takes the value 1 if there was 1 landing on A in these 3 landings. X takes the value 2 if there were 2 landings on A, and X takes the value 3 if there were 3 landings on A. So, how do we find that out? Okay, so what's the probability of landing in A in the first landing? Well, 0.6. What's the probability of not landing in A in the first landing? Well, it's 1 minus 0.6, which is 0.4. So we have to find the sample space in which there is no landing in A. And we have only one of those, omega 8. The 3 landings are in B, so that is the only space in which there was no landing in A. So basically we have to multiply the probability of landing in B times in first landing times the probability of landing in B in the second landing times the probability of landing in B in the third landing. The probability of landing in B is 0.4 times 0.4 times 0.4, and that gives us 0.064. Now, what's the probability of having only one landing on A? Well, we need to find these possible sample spaces. So in this one there is 3 landings on A, so no. This one 2 landings, no. Again 2 landings, no. Omega 4 has 1 landing in A, so this is one sample space that we are interested in. And omega 6 also has only 1 landing, and omega 7. So there are 3 sample spaces that apply to x equals 1. So what we need to do is to calculate the probability for each of the sample spaces and then add them. In fact, we have a trick. The probabilities will be the same. So instead of adding these 3, we can calculate only one of them and then multiply by 3. So, what's the probability of landing in A? 0.6. Then we multiply that by 0.4, and then we multiply that by 0.4. So that's the probability of landing on omega 4. So if we look at the others, omega 6, it will be 0.4 times 0.6 times 0.4, which is the same as omega 4, but in a different order. But multiplication takes different orders, so there's no problem. And the same for omega 7. 0.4 times 0.4 times 0.6. So if we do that, we obtain the value. So basically we have to calculate the probability of landing of the sample space omega 4 and multiply by 3, and that gives us 0.288. Now, what's the probability of having 2 landings on A? Well, we have to do the same. Go to the possible outcomes in which that we get 2 landings on A. Well, we find that omega 2 has 2 landings on A, omega 3 as well, and omega 5. So again, we've got three outcomes in which there are 2 landings on A. And we do the same. Let's take omega 2. The probability of landing in A is 0.6 times 0.6 times 0.4. And that, because it will be the same in the other 2 outcomes, so we have that, we multiply that by 3. And that gives us that the probability of having 2 landings on A is 0.432. And finally, what's the probability of X taking the value 3, which is that there are 3 landings on A? Okay, there is only one outcome in which that happens, which is omega 1, A. So we need to do probability of A, which is 0.6 times 0.6 times 0.6. And that gives us 0.216.